All right, ladies and gentlemen, welcome back to this Athenian Stranger tutorial video, where today we are going to work with the quotient rule to simplify some algebraic expressions. These expressions are rational in nature because they are fractions. Okay, so we're simplifying rational expressions using the quotient rule and, as needed, the negative exponent rule. Let's take a look at number one. Number one, we're given 28 p to the fifth over 28p. All right. Now in class, we implemented the quotient rule, and here's how we did it. First, we took care of the 28 by saying, well, 28 and 28 in the numerator and denominator, the greatest common factor is 28. 28 divided by 28 is 1. And we simplify all that by just canceling it out. And it leaves behind a 1. And then we dealt with the p's by using the quotient rule, which asks us to subtract the exponents when the bases are the same. A p by itself, or any letter by itself, is understood to have an exponent of 1. So all I have to do is write p to the 5 minus 1. And that gives me p to the fourth power. Okay, so that's number one. Number two is 42 into the fifth over 12n. And here I'm going to use a little bit of a different technique than the one shown in class. First, I'm going to prime factor 42 and 12 like this. Okay, 42 is an even number, so the first prime factor is 2, and 42 divided by 2 is 21. Then I'll break down 21. Okay, the first prime factor that I can use is a 3, and the other factor is a 7, and all those are prime numbers, 2, 3, 7. Now let's break down 12. It's even, so we use 2 and then 6. Then we break down the 6 into 2 and 3. So what I'd like to do is now break down n to the fifth power like this. Watch how I do this, because this is a little bit unusual. So I'm going to consider n using the product rule here as n to the fifth as n times n to the fourth. Okay, we know that n, it has an exponent of 1, so n times n to the fourth is just n to the fifth. So now I'll break that down and I'll put n. This is a very similar process to factoring numbers, but we're just writing letters. And now I put n times n to the third and break that down. N times n squared, and finally n times n. You see the similarity to factoring down to primes here? So we end up with 1, 2, 3, 4, 5 n's. And now what I'd like to do is rewrite this entire expression as the product of the primes. So with 42, I'll rewrite as 2 times 3 times 7. And then I'll rewrite n to the fifth as the product of its constituent variables, okay? Which would be n times n times n times n 5 times. So that would be times n times n times n times n times n. Right? So like I said, this is different than what we did in class. It works both ways, but I just want to show you this other way. Now I'll write 12 as the product of its primes, 2 times 2 times 3, and then n, okay, times n. And I just wanted to show that this is an option. Watch how this works. I'm going to search for pairs in the numerator and denominator. Here's a pair, the 2's cancel, and then here's a pair of 3's, the 3's cancel. All right, so now I'll rewrite as 7 times n. Ooh, one thing. So now the ns cancel as well. So I cancel one pair of n's. All right, so now I'll rewrite 7 times n times n times n times n. 7 times n times n times n times n. Okay? And then in the denominator, the only thing left is a 2, so I'll just write over 2. Okay, so far these things are all equivalent, and I'll just recombine now to say 7 n to the 4th over 2. So if we had simply applied the technique we learned in class, this is what we would have gotten, but I wanted to show you there's a different way to do it, right? It depends on the situation which way is best. This way is what we would call the elemental approach, and it breaks everything down to the smallest possible parts, and it always works. But sometimes it takes a little long. All right, so here's number 3, 35b squared over 35b cubed. All right, so if I use the technique we learned in class, we'll cancel the 35s and set this equal to b raised to the power of 2 minus 3. Okay, because we subtract the exponents. So that leaves us with b raised to the power of -1, and then we apply the negative exponent rule to write 1 over b. Okay, so for number 3, this is the reduced form. Number 4, 18 n over 14 n cubed. All right, remember there's a 1 there for that n, and I'll find the greatest common factor of 18 and 14. Okay, so we'll break down 18 as 9 times 2, and we'll break down 14 as 2 times 7. Then I can break down the 9 to 3 times 3. Okay, so I'm looking for any numbers in common. And the only one I see is 2. So the greatest common factor here, the GCF, is 2. So if I know that, I can divide 18 by 2 and 14 by 2 and simplify to 9 over 7. And now we deal with the n's. N to the 1 minus 3. Okay, this is understood to be multiplied. So that is equal to 9 over 7 times n to the -2. And we know that n to the -2 could just be written as 1 over n squared. So we'll rewrite this as 9 over 7 times 1 over n squared. And then we will simply multiply across the top and across the bottom. 9 over 7 n squared. And that's the most reduced form of the fraction that we were given. Here's number 5. -56 x over 48 x squared. Okay, so we've got to factor 56 and 48. And won't forget that negative sign either. I'm going to break down 56. You think of two numbers that multiply together to get 56. You might think of 8 and 7. And for 48, you might think of 6 and 8. All right, so the greatest common factor here would be the 8. And we'll try. We'll see if that is, in fact, the greatest common factor. All right, so we'll try dividing the top and the bottom by 8. So let's rewrite this. 56 divided by 8, remember it's negative. Don't forget that negative sign. 56 divided by 8 is 7. And we'll write the x. And then 48 divided by 8 is 6. And we'll write the x squared. And now we use the quotient rule. Rewrite negative 7/6 times x to the 1 minus 2. And that is equal to negative 7/6 times x to the negative 1. And we apply the negative exponent rule to set that equal to negative 7/6 times 1 over x. And we'll multiply across the top. We got negative 7 over 6x. And that's number 5. Moving right along. Number 6. We're given 36 n squared over 81 n cubed. Okay, so again, we got to think about greatest common factor of 36 and 81. And I'll prime factor this one. That would be 2 times 18. 18 is 2 times 9. And 9 is 3 times 3. 81, okay, the first prime factor is 3. So you need to know what 81 divided by 3 is. If you don't know that, you can divide. It's not multiplication or division that we learn. So you might want to run this. 3 goes into 8 2 times. 2 times 3 is 6. Okay. 8 minus 6 is 2. Bring down the 1. 3 goes into 21 7 times. So 3 times 27 equals 81. And we'll break down 27 into 3 times 9. And we'll break down 9 into 3 times 3. Okay, so if I'm following that pattern from problem 2 where I showed you that alternative method, I'm going to rewrite this as the product of the prime numbers. Okay, I'm going to give myself a healthy amount of space here in the numerator to write 2 times 2 times 3 times 3 times n for n squared. In the denominator, I'll write 3 times 3 times 3 times 3 times n times n times n. You know, and if you're following along with this, I want you to understand it's not an attempt to make the problem harder. It's an attempt to make the problem extremely elemental, okay? Broken it down to its smallest parts. And now we can cancel out our pairs. Okay, so I'm canceling out 2 pairs of 3's and 2 pairs of n's. And then we just rewrite what's left. In a lot of ways, you know, this is simpler than doing it by trying to find the greatest common factor or something. You're just writing down all the prime factors and you're multiplying them by each other. And in this way, you're kind of making the problem impossible to get wrong. And there's no chance for error here. 2 times 2 is 4. Over 3 times 3 is 9n. 4 over 9n. Okay, it's just an alternative approach, and in some cases it's necessary, in some cases it's not. What I meant to say earlier is this method of breaking everything down to primes always works. And it will even help us in higher level math. So it's good to know this method. All right, but we don't need that method all the time. Sometimes there's something so blindingly obvious that we can do that, like in number 7. In number 7, we are given 50 n to the 5th over 40 into the fourth. And so we can just, we can instantly see that the greatest common factor between 50 and 40 is 10. So we'll divide 50 by 10 and 40 by 10, and that will give us 5 over 4, and then we'll write into the fifth and into the fourth. Okay, and remember that's understood, this is multiplication. And now we'll apply the quotient rule. So when we apply the quotient rule, there is no more n's going into the denominator if the subtraction turns out to be positive. So let's just rewrite this, 5 over 4. Okay, and then in the numerator we'll write n to the 5 minus 4, which is just n to the first power, or n, right? So 5n over 4 is the most simplified form, and that's number 7. Here's number 8, and this is the last problem in the series, and that would be 10x to the 4th power over 45x to the 3rd power. Right, so if we're looking at the greatest common factor here, it would be 5. So we'll divide a 5 out of the 10 and a 5 out of the 45, and that will give us 2 over 9. And then I've got x to the 4th power over x to the 3rd power. Okay, and that is set equal to 2 over 9. Okay, and now we'll perform that quotient rule, x to the 4 minus 3. And that gives us 2/9 x. Okay, and you might see it in your answers as 2x over 9. It's the same thing, just written another way. Okay, well, I hope this video has been helpful. Y'all did really well on this today in class, so I feel like the mastery is fairly good. If you like this video, please give it a like. And if you have any questions, leave them in the comments. Make sure you've hit that subscribe button and notification bell so you're always updated when I drop a new video. Thanks.